Hey, math people. We're looking at lecture 2 here. We're going to call this more rates of change, which is just my fancy way of saying we can use the derivative in other contexts. This is the contextual application of differentiation, other than just particle motion. So this video is for you, Carl. Use the timestamps. Pause when you need to, and don't watch these videos from start to finish. You can dance around as you see fit. Be patient with yourself, and let's math. So, just a big old power round here. We got all these different contexts. What I want you to do is to interpret what the derivative means in each of these contexts. So what you want to think about is the units primarily. Maybe that's the first hint I'll give you. Like what would the unit of this 3,000 be if we're talking in the context of the number of people that live in a city is represented by P of t, where t represents time after the year 2000. If you want to take that a step further outside of just attaching the unit to these, try to write it as like a complete sentence of sorts. You know what? I'm going to do this. I'm going to give you the answer to the first one right now, and then I want you to practice with the other three maybe. So if you want to practice without that, I'm going to give you the answer to the first one in 3, 2, 1. So for the first one, you would say something along the lines of, at the start of 2024, right? Because 2000 plus 2024 is okay. So at the start of 2024, the change in population in the city is 3,000 people per year. I don't know why I was doing quotes that whole time, but that would be like a reasonable answer for number one there. If you have some issues with some of my semantics, I get it here, but I'm just trying to be precise to the exact, oh, well, technically, 24 would be January 1st, at midnight. Let's not get too technical with it. So try your best to come up with that for the next three as well. I'm going to reveal the answers in 3, 2, 1. Okay, so looking at 2 then, it says a leaking pool contains some number of gallons of water represented by a function g of t, where t represents time in minutes. So that g prime of 6 equaling -2, we would say something along the lines of, at exactly 6 minutes, the input, the pool is leaking 2 gallons per minute. And I chose to use the word leaking. You could say is filling up at -2 gallons per minute, which is much less natural, but technically is kind of true. So that's what my little personal spin on some of these. You can phrase some of these in other ways is really what I'm trying to drive home. But this is just kind of my particular phrasing. I fed these into GPT. If you wanted to just copy, print screen this and see what GPT's response, or any AI, you'll have iterations or variations of my answers here. So bottom line is you don't need to be precise with the language, right? All right, so but you need to be precise enough in respect to the units, and then the time value where you hit, the interpretation of the output of the derivative and the interpretation of the input in units. I would say that's probably where most people would stand. That this is 6 minutes because that is the input t, where t is in minutes. And then the output, well, since g of t was, what was g of t? Gallons of water, we're rateifying that g as g prime. So that would be, the rate of change, the slope of this gallon, in goes minute, out shoots gallon function, so gallons per minute. All right, a restaurant prices its pizza in dollars based on the equation P of R, where R represents the radius of the pizza in inches. So I'm going to assume the larger the radius, the more money they would charge. So P prime of 9 is equaling 1. This is interpreted as when the pizza has an exact radius of 9 inches, so input was radius, the cost of the pizza increases at a rate of $1 per inch of the radius. So my assumption here would be, as you get further and further out, your area would get larger and larger in a quadratic way, pi r squared. So, maybe if the pizza was going from 10 inches to whatever, just the rate at 10, it would be maybe a little bit more money because that's more area. that's sort of the interpretation here. So remember, this is a rate. This one is a rate, so that's $1 per inch of the radius, because r was measured in inches. And remember, this is, I like to like use the word like exact or at the start, because like right after that, at like 9.05, that rate could potentially change thereafter. So I say like exact. Some people don't really bother with that. Okay, the temperature, let's do the next one. The temperature of a room in degrees Fahrenheit is represented by T of P, where P represents the number of people in the room. So T prime of 8 is equal to 0.25. We would say when there are exactly 8 people in the room, the temperature of the room increases by 0.25 degrees Fahrenheit per person. So of course you can't have 8.01 of a person, but you know, there's a loose interpretation there that of course as you have more people entering a room, the temperature would increase more. Just body, we have temperature, body temperature, right? Heats up a room. Okay. And then just for the second round here, this is a pretty quick one, just simply introducing this notion that, yeah, indeed we can have different units, not just, meters per second. So here we want to use the provided information to come up with the rates of change, it looks like in every one of these scenarios, right? Whereas in scenario 4, you're just going to have to do a little bit of an approximation. Okay. So I'll show you the graph to each of these, but here's like the general rule for how you can practice them. Of course, just finding r prime of 2. Okay, here's the novice level. Novice level, you're simply just like from a contextual front, all right, not from a mathematical front. But remember, the whole focus or emphasis on this is the context. So novice level is you just find r prime of 2, b prime of 3, h prime of 3, and approximate w prime of 5. And that's novice level. Intermediate would be you not only just find, or not just, but you not only find the solution to these derivatives, but you also provide the proper unit for each of these. And then pro level is, can you like write it as a sentence in some way, referencing the initial time value or the input. It doesn't need to be time. I think actually in all these cases it's time. X represents, no, like the first one's not time, it's like pounds of material. So the pro level or advanced level is you give me the output of the derivative, you interpret it in terms of its units, but you also give me some sort of statement with respect to its input and that rate of change as like a sentence of sorts. So I'm going to just reveal the answer to all 3 of these right now. All 4 of these, 3 exact and then 1 approximation, right? So let's see how we do with that. So I encourage you to pause, give them a go. 3, 2, 1. So in terms of that novice level, right, just doing, you got a power rule for the first, you got a chain rule for the second, you got a chain rule for the third, and then you'd have to do an approximation for this last one with a time value or with the table. But let's read through these. So for one, it says a business revenue in dollars can be modeled by R of X that's equal to 400X minus 20X squared, where X represents the number of pounds of material used. So for R prime of 2, we got to find that and then interpret the meaning. So I found the derivative here just by doing power rule, and I plugged in 2 and I got 320. So the interpretation would be, when the business uses 2 pounds of material, their revenue increases at, what is this, $320 per pound. So here's kind of how this was meant to be written, 400x and then minus 20x squared. Imagine that you're selling some sort of product and you have to utilize a material. We'll change the x window for this just a little bit. We'll say like 30. And then we'll go y, we'll go from like 0 to, I don't know, 1,000. Let's do 5,000. Okay. So the idea behind this is that perhaps you're making some sort of object where if you utilize more material, it would utilize more resources, but people would be more inclined to buy it because it's like a better material, better object. It's not like some cheap flimsy object that can break easily. But obviously, there's some tipping point with that logic where if you use too much material, you're putting too much into the production. So then you're not maximizing that revenue. That there's this like hypothetical sweet spot. We're trying to optimize our profits here. This would be a very classic problem covered in like a business calc. Which is just like a variation of this course. So you can see here that we hit this like sweet spot where the interpretation here would be like with 10 pounds of use, you would see that kind of optimized output, which would be your revenue. So you're capping out at like whatever, this $2,000 maybe. But anyway, so if we're looking at the derivative at 2, okay, sure. Oops. Let's go ahead and plot it as well. So you can see here that, of course, if you attempt to kind of stop your profit at this value, well, the interpretation would be you're not making the material like strong enough. That if you were to make a higher quality object instead of using whatever this may be, 2 pounds of material, whatever the object is too, it's optimum to make it 10 pounds so that way you're not using too many resources. So like here, if you're using 20 pounds of this object, you're just spending so much money producing it that there's no return. It's loose, right? This is a very artificial setting for it, but that's the interpretation. All right, looking at 2. Your bank account that you deposited $1,000 in makes 4% interest per year. The amount of money in the account can be represented by some B of t, where you put in your 1,000, and then this is representative of 4% per year, just with a base of e. And then find b prime of 3 and interpret the meaning. So if you take the derivative, it's just via chain rule. Let's see what this value is. So, okay, so this is exponential growth, right? That's how savings accounts will work. The idea is that you generally don't make interest every moment, but instead every month, and but it's still exponential nonetheless. So this 39e to the 0.039 times 3. Times 3 up here. Times 3. Hello? Keep me up on the exponent, dog. I think you have to do parentheses for that. Times 3. There we go. So yeah, $43.84. So here's how we want to interpret this. At exactly the start of the third year, the account makes $43.84 per year. So really think about that, right? If you're making 4% interest on $1,000, you're going to make $40 right off the bat, or like within the first year, assuming that it's per year and not compounding monthly or anything like that. Remember, the focus here is on the fact that we're using different units. Try not to think too deep into some of the other reads of like, oh, well, technically, if it compounds monthly. Yeah, so we're just assuming it compounds yearly. So by the time you get to that like third year, at the start of the third year, you would have already made interest. So your interest is now making interest. So that's why it's $43.84, because it's compounding. Yeah, that's all there is to that one. So that one's exponential with the chain rule. All right, within 3, the height of the seawater in your favorite spot can be modeled by h of t, where 4 is maybe like that initial height, and then it's going to wave thereafter, plus 1/4 cosine pi t all over 4, where t represents time in seconds and h of t represents height in feet. So find h prime of 3 and interpret it. So finding that h prime is going to require a chain rule. That 4 goes away. This is sort of like the wave's initial height. You can think of it like that. So now we're just studying that rate by getting rid of that initial height. So yeah, what did we do here? We did chain rule, right? So we had this pi over 4 is a coefficient to t, so we multiplied this pi over 4 by 1/4. That's why we have pi over 16. Derivative of cosine is negative sign. And then we're just plugging in 3. So if you plug in 3 to this, lucky for us, it's 3 pi over 4, which the sign of 3 pi over 4 is a number. Is that positive root 2 over 2, right? 3 pi over 4. Yeah, that's square root 2 over 2, right? So this would then just be root 2 over 2 when you plug in your 3, and then 2 times that 16. So it's simplified to this value, whatever it is. It's going to be probably a pretty small value, would be my guess. pi times the square root of 2, two famous irrational numbers all over 32 here. Yeah, so that's pretty tiny. That's negative 0.139. And then what are the units here? Feet per second. So that's realistic to the context of the problem, right? Yeah, which you should always check for, right? Does it make sense in the context of the problem? If you got an outlandish answer for the number 2, like you make thousands of dollars in interest per year, you should really think about that off 4%, which is right now, it's 2025, roughly the savings, high yield savings account percent interest as of right now. Well, anyway, so that is, what's like what's 0.319 of a foot? Actually, I'm just going to multiply this by 12, right? Just to get this in inches. So, okay, this is about 1.5 inches, we'll say. So at 3 seconds, the height of the sea level changes. It goes down by like 1.5 inches per second. So, just kind of mellows out, kind of waves out, right? That's the idea. Is that if you were to graph this 4 plus 1/4, what is that, cosine? Cosine of pi t over 4. And I'll do it as x, right? Now, it looks like a flat line right now, but, so it goes anywhere between 3 inches above 4 or 3 inches below 4. It just kind of waves out. Okay, and then the last one. So let's go ahead and look at this table. The weight of a radioactive substance decays over time. The table shows the weight every 2 months. So who knows? Maybe you are a scientist recording this element. I would imagine you would probably have like a continuous understanding of this decay over time. But for whatever reason, you just have access to these snippets just every 2 months. So clearly here the weight is going down, so we do want a negative rate of change. The way that we utilize tables is we try to, you'll only ever be asked questions like this, at least in my class and on the AP exam, where if you're approximating like a derivative at a particular value, it's usually in between 2. So like 5 is dead smack dab in the middle of 4 and 6. So you would find the average rate of change there, which is a good approximation for the rate of change of this decay. So I did that average rate of change formula. I got negative 31. So W prime of 5 is approximately equal to negative 31. So the interpretation would be the weight of the substance at exactly 5 months. Yeah, but the word exactly here, since it's an approximation, is pretty useless. So we'll say at 5 months decreases by approximately 31 grams per month. We're probably going to assume this is some exponential decay, but just it's an approximation. It's the best we can do. Okay, so there you can do more with the derivative than just particle motion. That's it for this time, Math On.